polytropic process is a thermodynamic process that obeys the relation where P is the pressure, V is specific volume, N is the polytropic index, and C is a constant. All processes that can be expressed as a pressure and volume product are polytropic processes. Some of those processes are unique. This equation can accurately characterize a very wide range of thermodynamic processes, that range from n equals 0 to n equals, which covers n equals 0, n equals 1, n equals I cubed, n equals processes and all values of n in between. Hence the equation is polytropic in the sense that it describes many lines or many processes. In addition to the behavior of gases, it can in some cases represent some liquids and solids. The polytropic process equation is particularly useful for characterizing expansion and compression processes which include heat transfer. The one restriction is that the process should display a constant energy transfer ratio K during that process. If it deviates from that restriction, it suggests the exponent is not a constant. For a particular exponent, other points along the curve that describes that thermodynamic process can be calculated. Derivation. The following derivation is taken from Christian's. Consider a gas in a closed system undergoing an internally reversible process with negligible changes in kinetic and potential energy. The first law of thermodynamics states that the energy added to a system as heat, minus the energy that leaves the system as work, is equal to the change in the internal energy of the system. Energy entering the system increases the energy of the system, and energy leaving the system decreases the energy of the system. The sign convention is that heat transfer into the system is positive. Work done by the system is also positive. With this sign convention, the heat transfer term is added to, and the work term is subtracted from. Define the energy transfer ratio, or. For an internally reversible process, the only type of work interaction is moving boundary work, given by substituting the above expressions for, and into the first law, it can then be written. Consider the ideal gas equation of state with a well-known compressibility factor, Z, PV equals ZRT. Assume the compressibility factor is constant for the process. Assume the gas constant is also fixed. The PV equals ZRT equation of state can be differentiated to give. Based on the well-known specific heat relationship arising from the definition of enthalpy, the term ZR can be replaced by Cp, Cv. With these observations, the first law becomes where I cubed is the ratio of specific heat Cp/Cv. This equation will be important for understanding the basis of the polytropic process equation. Now consider the polytropic process equation itself. Taking the natural log of both sides gives, which can be differentiated and rearranged to give. By comparing this result to the result obtained from the first law, it is concluded that when the energy transfer ratio is constant for the process, the polytropic exponent is a constant and therefore the process is polytropic. In fact, the polytropic exponent can be expressed in terms of the energy transfer ratio, where the term is negative for an ideal gas. This derivation can be expanded to include polytropic processes in open systems, including instances where the kinetic energy is significant. It can also be expanded to include irreversible polytropic processes. Applicability. The polytropic process equation is usually applicable for reversible or irreversible processes of ideal or near-ideal gases involving heat transfer and/or work interactions when the energy transfer ratio IQ/IW is constant for the process. The equation may not be applicable for processes in an open system if the kinetic energy is significant. The polytropic process equation may also be applicable in some cases to processes involving liquids, or even solids. Polytropic specific heat capacity, it is denoted by and it is equal to relationship to ideal processes. For certain values of the polytropic index, the process will be synonymous with other common processes. Some examples of the effects of varying index values are given in the table. When the index n is between any two of the former values, it means that the polytropic curve will be bounded by the curves of the two corresponding indices. Note that, since notation, in the case of an isentropic ideal gas, is the ratio of specific heats, known as the adiabatic index or as adiabatic exponent. An isothermal ideal gas is also a polytropic gas. Here, the polytropic index is equal to 1, and differs from the adiabatic index. In order to discriminate between the two gammas, the polytropic gamma is sometimes capitalized. To confuse matters further, some authors refer to as the polytropic index, rather than. Note that a solution to the Lane-Emden equation using a polytropic fluid is known as a polytrope. See also, polytrope, adiabatic process, isentropic process, isobaric process, isochoric process, isothermal process, vapor compression refrigeration, gas compressor, internal combustion engine, quasistatic equilibrium, thermodynamics. References